Here's another example of thinking about Newton's laws and friction. In this case, let's put our little boxes over here, a 10 kilogram box attached by a string, and let's put a 5 kilogram box here attached by a pulley. And again, let's think about this pulley as being a perfect pulley, no mass, no friction, so it has no effect on the tension other than to change the direction. We think that these are tied by the tension, so if the 10 kilogram box moves to the right, the 5 kilogram box will move down. So we will set this coordinate system up so they're in the same coordinate. If the 10 kilogram box is x and y, it would move in the positive x. Let's rotate this coordinate system so that the 5 kilogram box would also move in positive x. So they're both going to be moving in the same designated coordinate. In this case, what I'm interested in is putting some friction here and trying to figure out like what is the mu, what is the coefficient of friction that's required in order to prevent these from moving. So obviously if there's no friction, the 10 would start to slide. If there's too much friction, it would stick. So let's find what is that coefficient that's needed. So our task is find mu, find the coefficient of friction. So what do? Well, we have our coordinate system. Not quite sure how to proceed, so we'll draw free body diagrams. Here's our 10 kilogram box, and here's our 5 kilogram box. And let's identify all the forces. On the 10 kilogram box, mg, force of tension, and normal force. And then there's also friction down here. So friction is going to oppose motion. If this is everything, then the force of tension pulls the box to the right. So that means force of friction must be to the left. All right. Over here we have force of tension on the 5 kilogram box pulls up, which means that mg is pulling down. And let's just remind ourselves of our coordinate systems. We're going to go x and y, and over here we're going to say x and y, which means that we can now put together our equations of motion. So we'll have two equations here, sum of the forces in the x direction and sum of the forces in the y direction. Over here we're only going to have an x equation because there's nothing going on in y. So let's just write down what we have. What's going on in the x? Force of tension is positive, force of friction is negative, equals mass times acceleration in x. In the y direction, force normal is positive, mg is negative, equals mass times acceleration in y. Over here we have force tension is negative because we said down is positive. So we're going to say negative force tension plus mg equals mass times acceleration in x because that's our x dimension. All right, so there's our equations, there's our everything we know. The easy thing, even really without thinking, the easy thing that I can do is I can say the acceleration in the y direction here, nothing's going on. Acceleration is 0, which means that normal force is equal to mg. And for now, you know what I'm going to do? Instead of putting in 10s and 5s, let's label this box 1, and let's label this box 2. So we'll say this is m1g. Okay? So what that allows me to do is I remember force of friction is mu F normal. I know I'm going to have to use this somewhere since I'm looking for mu. Right? Since I'm looking for mu, this is going to come into play. So let's make that substitution. Let's just put that guy right there, and we can say force of tension minus mu F normal equals m1a. So force of tension minus mu m1g equals m1a. And then over here we can do our labels again as well. Minus force of tension plus m2g equals m2a. Okay, so here's my two equations, and now I need to think about what do I actually trying to find. I don't know force of tension. I don't know acceleration, I don't know mu, so I don't know three things. I'm going to figure out, I'm going to think a little bit about what's going on. In this case, if I'm trying to find mu in order to see if they move, I can see in this equation, if force tension is bigger than force friction, it's going to slide to the right. Right? If force tension wins, force friction loses, it's going to slide to the right. And if I look down into the equations, force tension is bigger, then this acceleration will be positive. Makes sense. So here I can look at if force tension is smaller, then it wouldn't be able to move. Really what I'm looking at is my condition, and my condition will be, my boundary condition is the acceleration equals 0. Right? If the acceleration equals 0, the force tension exactly balances the force of friction. That's going to be the boundary between moving and not moving. So I can follow this through and find acceleration equal to 0, set that condition, follow this through, set that condition. That allows me to easily calculate force tension equals mu m1g, and over here, because of my condition, force tension equals m2g. So these are true only for my condition, right? If the acceleration is 0, then that's going to be my force tension, and I can easily then put those together, and I can say mu m1g equals m2g, and solve immediately for mu. That's going to equal to m2 over m1. So I have this relationship now. Mu totally depends on the two masses. So if I go and plug, and I can go ahead and plug that into from my equation. So over here for me, I have m1 is 10 kilograms and m2 is 5 kilograms. So for me, mu has to be 5 over 10, or 0.5. If the coefficient is 0.5, then force of tension will exactly equal the force of friction. The acceleration will be 0. If it's not moving, it'll keep not moving. And this makes sense. So we can sort of extend this a little bit. What if this is really small? What if there's only 1 kilogram here? If there's only 1 kilogram here, then m2 over m1 would be 1 over 10, so which would mean mu would be 0.1. I would need less friction if there's less weight. If there's less difference between them, I would need less friction. So conceptually, it also makes sense that my friction relationship is m2 over m1 for this particular scenario.